we're going to start looking at kinematics now in two directions. So things that move through the air in both the horizontal and the vertical direction. Okay? Does anyone know what that's called? When something moves through the air in both a horizontal and a vertical direction? Right, it looks like this. An arc, yeah, or a projectile. Right, if something is projected through the air, it starts moving in two dimensions or two directions. So that's going to be kind of what overall Chapter 3 is about, projectile motion. But we have to look at basically breaking everything down into the x direction and the y direction first. Okay? Because in physics and in our equations, we can't deal with things at angles. Okay? We can't deal with things at angles. We have to break them down into their x component and their y component. So that's what we're going to focus on today, is breaking down these measurements and these velocities and displacements, whatever they are, into its x and its y components. Okay? So, does anyone remember what a vector is?
Something with direction and magnitude.
Yeah, it has to have direction and magnitude. So vectors are any type of measurements that have to have both magnitude and direction. And we deal with vectors almost exclusively in this class, right? What's the other version of a vector called? Like without direction. Do you remember? No, a scalar. Good. Okay. So scalar is the opposite of a vector. Not really opposite, okay? I say that, but it's not a true opposite. It's the counterpart to a vector, but it's much less used, right? We focus almost exclusively on vectors in this class. And those vectors could be in the form of displacement, velocity, or acceleration. Those are the three we've looked at so far that would be considered vectors. Okay, there's also forces, which will be the other vector that we really look at. Most of them will be some version of velocity or acceleration when we get into circular motion, things like that. But these are the three we've looked at so far. So vectors have to have magnitude and direction. Scalars only have a magnitude, right? They have no direction. And they always are a positive number because the negative for us indicates direction. Okay, the negative indicates direction for us. So vectors can be positive, negative. They can be north, south, east, west. They can be at an angle. Degrees, right? Northeast and southwest, things like that. Scalars don't have that issue. They don't have any direction that goes with them. Okay? So examples of scalars we've looked at so far are speed, distance, time, and temperature. Okay, temperature is kind of an iffy one because it has a negative, but that doesn't have anything to do with the direction. Right? That's the value of the number itself, the magnitude itself. Do you remember how we represent vectors? How do we draw vectors? Do you remember?
A line and an arrow.
Yeah, that's right. It's an arrow. So when we deal with vectors and we deal with motion diagrams, we represent a vector with an arrow. Okay, all vectors are represented with arrows. Okay, and we try to draw them to scale, and we have to draw them in the correct direction. Okay, so did we talk about what drawing to scale means? Or not so much? If I have a vector that says I go 10 meters north, and I have a vector that says 5 meters north, are those two drawn to scale? No, why not? Right, the 5 should be half the length of the 10. Right, that's what we're talking about when we say drawn to scale. We're going to practice drawing exactly to scale, like using a ruler and developing a scale to draw these vectors. But on most of our problems, our scale can be extremely simplistic. Okay, as long as we're proportionally using a scale, we're good to go. Right, which means if we have a 2.5, it needs to be, again, half the size of that 5 meter. Okay. There's going to be times where I ask you to get out a ruler and use an actual scale, but most of the time when we draw our vectors, we're looking at a proportional type of a scale, a ratio type of a scale. Does that make sense? Okay, so one vector needs to be to scale in comparison to another, is what we're saying. Okay. Vector arrows are drawn with what we consider a tail and a tip, right? Which side do you think would be the tip? The arrow side, right? This is called the tip. And this is called the tail, right? Who never knew arrows had so much information about them, right? Okay, tail and a tip. And that's important because when we add vectors, we're always going to draw them in the direction of the motion. So the tip goes in the direction of the motion. And we're going to add them graphically using something called the tail to tip method. Okay, we add vectors using something called the tail to tip method. So what do you think the name of that method, what does that tell us we're going to be doing with our vectors? That's right, the tail of the second touches the tip of the first. Okay, so when we're adding them graphically, let's say we go north, then we go east, then we go north again, then we go west, then we go south, then we go east, right? That's our path of motion. Here's where we started, and here's where we're ending up. So if we want to find our total displacement, right, we're looking at our origin from to the tip of our last vector, right? So if I want to find displacement, or I want to find how far did I end up from where I started, that's how I'd go about that. If I wanted to find the distance, then I'd find the math along each of these vectors, right? But I don't care about the distance so much. I care about the displacement. Okay, does that part make sense? Okay, so tail to tip means simply I'm going to add the second vector to the tip of the first. Okay, it wouldn't look like this, right? If I go north and then I go east and then I go south and then I go west, right? That doesn't show me a path. That's not leading me anywhere. Okay, so I'd go north, then east, then south, then west, right? That's leading me somewhere from my origin. It's allowing me to view a displacement from my origin. Okay, and that's really important when we add these vectors. Questions here? Okay, so that's called the tail to tip method. Okay, so let's try this one. If a person walks 8 kilometers east, then another 6 kilometers east, right, what's my final displacement? 14 kilometers east, right? I just added those graphically, and this is a really simplistic problem, right? They're both going in the same direction. There's nothing complex about the motion. That seems like putting them into a vector form is a little bit unnecessary, right? But when we get multiple vectors going in multiple directions, we'll see how it can be helpful. Okay, so same direction, right? We're just adding them right on top of each other. Different directions, we still add them right on top of each other. Okay, tail to tip. The resultant vector is what we consider to be the sum of all of our vectors on a motion diagram. So the resultant vector is the sum of all vectors. Okay, and it's not just the addition sum, it's the sum of all of our vectors at certain angles and at certain directions. So, oops. And what I want you to know about the resultant vector, I didn't write it here, but I want you to write this down. Okay, it's always drawn from the origin to the tip of the final vector. Okay, so the resultant vector is always drawn from the origin to the tip of the last vector. So the resultant gives us our displacement, okay, or our average velocity, or our average acceleration, whatever it may be that we're looking for. It's going to give us the overall of all of those vectors, right? That's what the sum means, the total of all those vectors. But here we're adding them with direction and everything, okay? So it goes from the origin to the tip of the last vector. Suppose a person walks 10 kilometers east, then walks 10 kilometers north. What is the resultant? Okay, so whenever I start drawing vectors, I like to put a little crosshairs so I know where my starting point is. Because if you get 12 different vectors, it's kind of hard to go back and find your starting point. Right? So I put a little crosshairs so I know where my starting point's going to be. Okay? And I don't have to add them in any particular order, because if I go east 10 and then north 5, right, doesn't it get me to the same location as if I would have went north 5 and then east 10?
Yep.
Right, it gets me to the same place. So the order in which I add my vectors makes no difference. So it's just the easiest to just add them in the order you receive them. Right? We went to east first and then north. So this would be 5 and this would be 10. So I've only got 2 vectors here. My resultant goes from where to where?
Origin to the tip of the final.
Yep, origin to the tip of the final vector. So this can be labeled V sub r for resultant vector, or d sub r for resultant displacement. However you want to label it is fine with me. Okay, it does not matter. Okay, essentially here what we're doing is finding the displacement, because we walked this many meters east and then this many meters north. We want to find out where's our ending point, right? How far away are we from where we started? Okay, so how would I go about solving this side of my triangle? Pythagorean theorem. Why don't you go ahead and do that? So you need your calculator out today if you don't have that. For our hypotenuse here, or our final displacement, 11.18, and what's our units? Kilometers. So, this tells us how far we are from where we started, but it doesn't tell us, if I was going to leave my origin and try to make it to this spot, I don't know which direction to go, right? So, how do I find out what direction I need to go? Right? I'm going to find this angle so that when I leave my origin, I can say, okay, I need to go 30 meters northeast, or 30 degrees northeast, or whatever it is. So this is not complete without the angle that goes with it. Okay? I don't use law of sines or law of cosines or anything like that. I use regular sine, cosine, tangent. So that's how I will always do it. Okay? So here I like to use the numbers I was given. So I was given the opposite and the adjacent side. When I'm finding my angle, I'm going to have to use second, right? Whenever we look for the angle, we use that second function, opposite over adjacent. So I would use second tangent of 5 divided by 10. And I get an angle of 26.6 degrees. Yeah, make sure we're not in radians. We need to be in degrees. The mode on your calculator needs to be in degrees if you're not getting what I'm getting.
So why did you say we can't use just normal tangent on that?
When you solve for the angle using a trig function, you have to use the second button.
Okay.
If you solve for a side, you don't have to use the second button.
Got it.
Okay? So anytime we solve for an angle, we use the second.
Do you have to have like north or
Yeah, that's what's going to come next. So we've got the degree now. Now is it 26 degrees what? Southeast, northwest, what is it? Northeast, but it has to be even more specific than that. Northeast could be anywhere, right, in this direction.
north of east? Is that
Yes, we have to have north of east or east of north. So which one is it? North of east. Okay, so how many of you are unsure about how we came about with that north of east? And that's fine if you are, because a lot of people have trouble with that. Okay, so here's my trick for teaching north of east or east of north or whatever it is, right? Because east of north would be this angle right here. Right, if our triangle went this way, this angle would be east of north. Okay, so we need to know the difference between those two. This is my trick. I look at what axes is my angle touching, right? If this is the north axis, east, south, and west, which axes is that angle touching? The east, right? It's touching the east axis. It's only going to touch one of those cardinal directions. Then you decide, does our triangle go north of east or south of east? Right, it goes north of east. That's my little trick for that. If you can just look at it and see it, that's great. Some people can't. Okay. Vectors can be added in any order. We can add any number of vectors. It doesn't matter how they are. The resultant always goes from the origin to the tip of the last vector. So I did have it on there just a little bit later. And we already talked about these, so just write them down if you want. You don't have to, but we can add any number. We can add them in any order. The resultant always goes from the origin to the tip of the last vector. So if we're looking at this little diagram here on the right, which of those is my resultant vector?
The left.
Right, the red one. Yeah, the left one, right? For this one, I want you to come get a ruler. I have rulers up here. And you're going to add these graphically, okay, to scale. So you're going to pick a scale. Okay, I gave you an example. 1 centimeter equals 10 meters. You're going to draw them out on your paper. So you need to leave yourself a little room on your paper. Draw them out Does it matter what order you draw them in? Nope. Doesn't matter what order you draw them in, as long as you draw them tail to tip. Okay? Then to find your resultant vector, you're going to measure from your origin to the tip of the last vector and convert that back using your scale. So you're going to give me a final resultant vector in meters. All right, so if we have it drawn graphically, does it look something like this? Okay, I didn't draw mine to scale, but when we measured our resultant vector, why don't you give me some measurements that we had? Raise your hand and give me some measurements. We'll see who ends up being close. Yeah, Colin.
63.
63 exactly. Okay. What? 60.7? That's what you had? 6.7 what?
No, it's just 6.7.
I want it in meters. 62.5. Yeah, Danny. 64. Okay, anyone else? Yeah, Johanny, what'd you have? 58. Alexis? 67.
You're my favorite.
65. Right, so we got some numbers all over the place, and you guys were all given the same information, right? Okay, we'll see. Okay, so now we're going to find out how to mathematically solve it. Okay, listen, we're going to find out how to mathematically solve it. We always deal with right triangles, so we're just going to build ourselves a little right triangle here. All right, we're going to build a right triangle, making this resultant the hypotenuse. Does that make sense how I did that? Okay, this is mathematically how we could solve for this. So my vertical side, or my y side, would be 10 plus what? How long would that side be?
60.
Right? If this whole side is 100 from here to here, and this is 40, that means this side is 60. And my x side is what? 20. Okay, so let's solve now for the hypotenuse of that triangle. Do we see where those numbers came from? 60 and 20. Okay, so let's solve for that hypotenuse. $63.25 meters should have been our final. So we had some that were pretty close, right?
67.
Sometimes people's measuring skills are a little
I got 22.
22, okay. That's no good.
No, I mean for your. Sorry.
This side is 50, minus 30 is 20. Well, I'm showing you how to do it mathematically, so, okay. Listen, okay? Now we've got our displacement, we need our angle. We always want the angle that touches the origin. Okay, so we want this angle here. Okay. If our sides are 20 and 60, we're going to use second tangent of opposite over adjacent. 18.4 degrees. Do we agree there? About 18.4? And what is our east of south? Very good. Okay, because that angle is touching the south axis, right? Then we decide, does it swing east of south or west of south?
So,
Okay.
on a test, if I had 71.6.
Also acceptable. Okay, so Braden just asked if he had solved his triangle this way, right? This angle would then be 71.6 degrees south of east. Also acceptable. It's going to get you in the same spot. So this complementary angle, is that complementary or supplementary? Complementary angles will work. They just have to be labeled with the correct east of whatever or south of whatever. Given vectors, how do we start breaking them into their horizontal and their vertical component? Okay? So if I say a plane or something is moving 35 meters per second at 20 degrees north of east, how do I find its vertical component and its horizontal component? Right, that's what we're looking at. We're breaking down these vectors into its horizontal and its vertical components. Okay, so this we would call V sub y. Why would we call it Vy? It's on the y-axis, right? So all vertical things are labeled with a y. All horizontal things are labeled with an x. Okay, so let's try to solve for these, just for fun. Okay, if I'm trying to solve for Vx, is that adjacent or opposite of this 20-degree angle?
Adjacent.
It's adjacent. And we also have what side? The hypotenuse side. So adjacent and hypotenuse would lead us to what trig function? Cosine. So I'd set it up like this. Cosine of 20 degrees equals the adjacent, which we don't know, over the hypotenuse. Right? How do we go about solving for Vx there? Don't we just multiply them? Right? So have you ever seen them written in this notation, 35 cosine 20 equals the adjacent side? Okay, good. That's how I'll write it pretty often, right? Because it's always times the hypotenuse. So that's why I'll write it like that. All we're doing is multiplying 35 over times 35, right? So you'll see me write it like that often, okay? So 35 cosine 20 is equal to 32.89, right, meters per second. And is our component going in the positive direction or the negative direction? The positive, so it gets to stay positive. Okay, so here's something that's really important about breaking down vectors into components is that you have to include the negative if it's going west or south. Okay, north or east gets to stay positive, west or south gets to go negative. So go ahead and solve for V sub y by yourself. Solve V sub y by yourself. I would use the numbers you're given, not the number you solved for. So although now you do have that x side, I'd go ahead and still go back to the hypotenuse and the opposite side now, which would lead you to what? Sine, yes. So 35 times sine of 20 is equal to 11.97 meters per second. Okay, the components always have the same unit as your hypotenuse, or as your resultant vector.
Do we need a negative or wait, we didn't find it for one.
Yeah, we didn't end up finding, we didn't need these, we don't care about the components that go through. So we don't need a negative because we talked about the angle of it.
Oh, okay.
Okay. If our resultant was purely west, we could put a negative there instead of a west or whatever.
Oh.
Yeah. So Amanda asked a good question. On our last problem with our graphic resultant, we don't have to put a negative there because it's going southeast because we included the direction. The cardinal direction counts. If you don't include the cardinal direction, you need the negative or a positive. But whenever it's at an angle, we don't include a negative because the angle itself is telling us the direction. Okay, are we good with our trig functions, sine, cosine, tangent?
Yeah.
Okay, I think everybody looks pretty good on this. Okay, a helicopter's flying 34 meters per second at 25 degrees south of west. What are the components of the velocity vector? So I want you to solve for x and y by yourself. All right, can someone raise their hand and give me an answer for finding x, v sub x? Yeah, Jake, what'd you have? 30.81. Raise your hand if you agree. Raise your hand if you disagree. Why do you disagree? Has to be negative.
I have it written down.
You didn't tell me, though.
I just wasn't sure.
Yeah, it has to be negative. So, yeah, that is part of the answer, so that's important. Okay, what about for v sub y? Yeah, Alexis, what'd you have?
Negative 14.37 meters per second.
Perfect. Okay, perfect. So here's the deal. You either need the negative or the west, but not both. Right? You don't need negative 14 meters per second west. That kind of cancels out, right? We want one or the other, but not both. Okay?
So it wouldn't be wrong if we did west and south.
That's right. It would be fine if you just put west and south. Yeah.
I thought he said west.
No, you're gonna fit. So good.
So,
Okay, a vector represents a displacement at 500 meters at 30 degrees north of east, where the magnitudes of the vertical and horizontal components. So now you have to draw the vector and then break it down. Okay, so this is the skill that you have to develop well. Draw the vector and then break it down. So 500 meters at 30 degrees north of east.
isn't this like normally we would want to have a protractor or something?
No, you don't need a protractor. We don't have to draw our angle perfectly. This is what I'll show you. This is what I'll tell you. I always start with my crosshairs, so I know where my starting point is. I know north of east goes generally, right, in the north and east direction. So I'm just drawing a kind of arbitrary vector there in the north and east direction. Okay, if it's north of east, where does my angle need to go? On the top side or the bottom side of that vector? On the bottom, right? So we want it to touch that east axis. So I just go, put my 30 right in here, right? And then I draw my triangle to complete that, right? That's how we go about drawing our vectors. Okay, usually components are drawn with dotted lines since we know they're not true vectors. But that's not going to be something I'm going to count off for, but it's just something to think about. Okay, and then where does the 500 go? The hypotenuse, good. Okay, so why don't you go ahead and break that down. So when we draw it, we start with an arbitrary vector in that direction, we decide where our angle goes, and then we fill in our triangle.
I got 433.01 meters.
For your y, I think it should be smaller than that. Okay, 433 point. Okay, and what about y? 250. Okay, so as we look at it, we've got a relatively small angle here, right? Mine's probably not drawn to scale in terms of the angle, but as our angle gets larger, our y component should get larger. So we need to make sure that our scale kind of works there, right? 30 degrees would lead us to a small y component and a big x component. Okay? And our units, would be meters. Do either of those components need to be negative? No. Okay. Very good. She drives 22 kilometers in a northerly direction, which means north. Okay, not like meandering north. Okay. She drives in a direction 60 degrees south of east for 47 kilometers. What's her displacement from the post office? So I'm going to show you what it looks like when we do the vectors, but for this one, we're literally just going to use vectors as individuals, and we're not really going to worry about the diagram as much. Okay, you can draw the diagram, but we're not going to worry about it to scale and doing all that kind of stuff. Okay, so this is basically how we add vectors mathematically, right, rather than graphically. If we were to draw it like this, our resultant would go here. Oops. Our resultant would go with that black line, right? And that's how we would go about finding our resultant graphically. Okay, but it's a little bit complex because we've got an angle up here going on. So what we're going to do is we're going to add them mathematically instead. Okay? So for our first vector, which I labeled as d sub 1, right, when we add them mathematically, we're just going to deal with each individual vector. Okay, so d sub 1 looks like this. It's drawn purely north. So that means its x component and its y component, we're going to break each vector into x and y. Does it have any x component at all? No, right? Because it's going purely north. Now what about its y component? What is the value of its y component? 22. Okay, and is it positive 22 or negative 22?
Positive.
Positive 22. It's positive 22. That's important. Okay, now our second displacement vector, right? We're not looking at that. We're kind of resetting our origin here. Okay, and it said it was 60 degrees south of east. So that means 60 degrees goes here. That's what our second vector looks like. Okay, does that make sense? I can draw it a little bit prettier too. That's probably not the best drawing, but we're going to draw all of our vectors separately. So here's 60 degrees. And our hypotenuse here is 47. Okay, so does this make sense? We're taking each individual vector, we're breaking it into its x and its y components. So knowing what we know about this triangle, can we break it into d2x and d2y? Yes, we can. Okay, so this is really d1x and d1y up here. Okay, so each vector now has an individual x and y component. So d2x would be the cosine. So 47 cosine of 60, which is 23.5. Can our x component remain positive, or does it need to be negative? The x is positive. It's going east. 47 sine of 60 for the y. I got 40.7. Positive or negative?
Negative.
Negative, because it's going south. Okay, so we're taking individual vectors, breaking them into x and y. Now to find our resultant vector, which essentially would go from origin to the tip of the last vector, right? It would go here to here. Right? That's what our resultant should look like. We're going to add the x's and then add the y's, and we're going to build a new triangle with those components. Okay? So let's, oops. Go back here, maybe? Okay. We're going to add our x. So let's say d resultant x is equal to 0 plus 23.5. And the resultant in the y direction is 22 plus negative 40.7, right? Or 22 minus 40.7. So now these are the components of our resultant vector. They're the components of our resultant vector. They're going to allow us now to build a new triangle with our resultant. Okay, so we're adding these mathematically instead of graphically. So I'm going to draw that over here, what it would look like. Okay, so these are the components. These are the sides of our resultant triangle. So here's my starting point. My x is positive, 23.5. My y is negative 18.7. You don't have to include the negative when you draw the vector, because the negative is just telling us downward. And our resultant looks something like that. Do these two look alike? Does the resultant look like it should? Yeah.
Are we going to have to draw that every time that we're trying to find a component, or do we just put the answer?
Yeah, you're probably going to have to draw this whole thing out. Okay, just so you don't get lost. Okay, because it's quite a process.
When you're solving it, you don't have to put negative 18.7.
Nope, when you're solving it, you don't put negative because it's just the direction. So solve for the hypotenuse and the angle. Excuse me.
For displacement, you can't do like distance formula for like 0 from like origin to whatever. I'm gonna screw this up so much.
They're long problems, but once you get down kind of a rhythm, you'll be fine.